Hello everybody, my name is Alejandro Cuevas. I'm a PhD at Carnegie Mellon University. I'm here with my co-author Fieke Miedema, who is from TU Delft, and together we are going to be telling you a little bit about accuracy of online marketplace measurements. This is work with our colleagues between CMU and TU Delft. So to start this talk, I will assume that all of you law-abiding citizens haven't had the chance to interact with a darknet marketplace. So on the screen we have Hansa, a marketplace that existed between 2015 and 2017. The website is similar to other online marketplaces with category filters and sorting options. However, Hansa was a marketplace where mostly illegal goods and services were commercialized. On the sidebar, we see various types of drugs, fraud-related items such as credit cards and database leaks. We have tutorials ranging from how to manufacture drugs to how to deploy malware, services such as DDoS and bulletproof hosting, and digital goods such as malware and phishing kits. And since their emergence in 2011, the question of how big these marketplaces are attracted the attention of academic researchers and law enforcement agencies. D&M measurements influence various aspects of law enforcement. Estimating how much revenue a marketplace or vendor drives is useful to prioritize which market or vendor to go after, and is also used during the indictment. D&M measurements and research also informs policymaking. In the US, for example, a bill was introduced to increase efforts against trade in dark web marketplaces with a focus on opioids. But how do we find out, for example, whether opioids constitute a lot of sales in D&Ms? Because D&M research plays a role in judicial and legislative proceedings, it is vital to have accurate and validated measurements. To understand how previous work estimates revenue, we need to navigate to a listing page, as the one seen on the screen. In this page, you will usually find the price, the vendor, and most importantly, customer reviews with timestamps. Reviews are what allow us to estimate a lower bound of revenue. D&Ms usually strongly encourage users to leave reviews for vendors because it's the only way to build reputation in these anonymous markets. And past work has relied on the fact that reviews seem to match orders, and thus by assuming that each of these feedbacks what was an order and multiplying it by the listing price, we could get a lower bound estimate on the amount of revenue that listing generated. So when measuring marketplaces, we're not directly measuring the object we care about, in this case orders, but instead we're measuring proxies, in this case feedbacks. And the problem is that there's a substantial body of work on darknet marketplaces based on measurements by proxy, but with little validation. Furthermore, these studies rely on crawls or scrapes to gather data, but we have little insight on how reliable scraping is or what proper scraping methodology should be in these markets. So we sought to get an empirical understanding of the losses and biases that exist by comparing back-end versus scrape data. And we test the effectiveness of various scraping designs and coverage estimation techniques through simulations.
The challenge is thus to approximate the backend by front-end measurements. This is often done by scraping the HTML from the web pages. These are then processed by doing steps such as parsing, deduplicating, and matching reviews to listings. This then results in a database of unique reviews, listings, and vendors that can be used to approximate the backend. From this data, researchers attempt to measure things such as market revenue, vendor security practices, through inference techniques. The inference techniques applied differed between studies, as did their processing steps. The perennial question is, how good are these measurements? Some researchers have attempted to answer this by validating their measurements in a variety of ad hoc approaches: identifiers, court cases, metadata, and abundance estimation. However, these works have lacked consistency in their approaches, in their documentation, and validation. This prevents us from understanding the losses that may occur at each step of the way, such as the collection loss from scraping and processing to the inference loss from using proxies. Our goal was thus to study the accuracy of current measurement approaches and find directions for improvements. To do this, we leveraged scrape and backend data sources. CMU Scilab scraped Hansa Market 14 times, so 14 snapshots, over the 2015 to 2017 time period. Similar to previous work, we combined all these scrapes and we processed them to get a database with listings, reviews, and vendors. We were also granted access to the Hansa backend, seized by the Dutch National Police in their sting operation. The database contained the latest state of the backend as well as multiple backups. By trying to match each object from the scrape database to a corresponding object in the Hansa backend database, we calculated coverage. How much of the backend database was captured in the scrapes? We found out that if you take the backend as a 100% ground truth, 54% of all objects are captured in the scrape. This means that the empirical collection loss on Hansa was 46%. We know that this can happen because listings get deleted and reviews can be hidden by vendors. In what way is a scrape then truly a random sample of the total population of available objects? For that, we need to take a look at the scraped and not scraped listings. Why listings? Well, differences between scraped and not scraped vendors and review come down to whether the listing is scraped. Because if you don't scrape the listing, you don't know what the vendor sold, and you don't know the price of the item that the review belonged to. So for listings, we explored features that could be correlated with the chance of an object being scraped, such as the listing being hidden, and features that influence revenue calculations, such as price. We found significant differences for multiple features. For price, scraped listings are on average lower priced than not scraped listings. For the number of reviews, scraped listings often have more reviews than not scraped listings, which could point in the direction of the scrapes already being biased towards popular listings. Finally, the Hansa scrapes often contain more digital goods listings, while not scraped listings were more often from the wheat category. This is interesting because both categories were of equal size on Hansa. So we know that the empirical collection loss of Hansa was 46%, and we know scraped listings are biased. So what does that then mean for our revenue calculations? We've looked at the total revenue of Hansa. When we calculated the revenue from all the transactions and orders, it added up to 50.1 million. So we're going to compare all other revenue calculations against this as ground truth. What we saw is that if we calculated revenue just based on the reviews that were scraped, it only amounted to 13.2 million. We call this the observed revenue. However, we know the collection loss, 46%, which means that only around half of all the reviews were scraped. When we then calculated the revenue of all the reviews that were available in the backend, we could explain another 14.2 million in revenue. This is the revenue that we missed due to the hidden reviews, partial scrape, rate-limited scrapes, timeouts, failed captchas, etc. Collection loss. If we had scraped perfectly, capturing all reviews, we would thus have captured a bit more than half of total revenue. But using reviews to calculate revenue is still using a proxy. In reality, not every buyer leaves a review. Some buyers buy more than one quantity, and buyers also pay for shipping costs. When we calculated the revenue based on actual transaction and order data, it explained 22.7 million. Thus, by the need to infer orders and their transaction price from reviews, you miss, again, almost half of revenue. This is the inference loss. Summarizing, our results show that the current measurement approach on online marketplaces introduced significant collection and inference losses. However, ground truth data like we had is rarely, if ever, available, and scraping captures more versions of one object.
Now, we had a good understanding of the shortcomings in our Hansa scrapes, but we wanted to know how we could have done a better job. And to do this, we created a simulation. At a high level, we simulate events that could occur at a given day in the lifetime of the market. For instance, the probability of sampling a new listing is really high at day n. And at day n plus 1, we might have a chance of sampling the new event listing. And we do this a certain number of times each day. And we have a few other events that we define in our model, but essentially what we're doing is using the data we have about how the market grew over time to create similar markets that we can run additional experiments on. In particular, we wanted to try other scraping approaches, and we define a scrape basically as a sample of visible items. And this allows us to measure the coverage of different scraping approaches under different assumptions and can also be extended to imitate other markets. DNMs seek to prevent scraping. And given that several past studies have relied on only 1 or 2 scrapes, we used our simulation to test how good you can expect your coverage to be with different request limits. And it turns out that to achieve high coverage, you need to be making almost 1 request per second. So if you're using a stealthier approach to scraping, how many scrapes would we need to achieve decent coverage? And does it matter whether we had a consistent routine or if we scraped at different intervals? In the case of our simulated Hansa, only after 10 stealthy scrapes we achieved an average coverage of 53%. On the other hand, whether we scrape exactly at even pace intervals or at random intervals didn't matter too much for Hansa. However, other markets delete feedbacks after a number of days, and in those cases, a consistent routine is crucial. And given that stealthy scraping involves using a reduced scraping budget, we tested a simple scraping algorithm that split its budget between discovering new pages and rescraping popular pages. And this worked as follows. Let's say we discover at time t 2 similar listings. Then at time t+1, we rescrape each listing and compute their popularity. The golden cigarettes, in this case, gain more reviews, so we keep it in a popular list. Finally, at time t+2, our scraper only rescrapes the golden cigarettes and not the silver ones. Instead, it uses its budget to discover new listings. With this strategy, we capture an average of 9% more unique objects. And this strategy could be applied in any context where we believe the object we want to measure is not uniformly distributed. Our study provides a new lens for past studies and a framework for future studies. First, we identify a lack of consistency and methodological description in previous D&M studies, which we show limit our understanding of losses and biases that may exist. Second, through our empirical results, we quantify the sources and magnitudes of biases and inference losses on our scrapes, which can be used to contextualize past studies, as well as to improve calculating upper bounds on future studies. Third, we define a simulation model, which can be used in other marketplace contexts, and which enabled us to 4, test better scraping designs, and 5, validate previously used validation techniques. We didn't get to cover this last point, but we invite you to check the details in our paper. Thank you very much, and we look forward to your questions.